All right, so the next talk is also on inductive program synthesis, and Yoon from Seoul National University is going to tell us how to do that using forward-backwards abstract interpretation.
Yeah. Hello, everybody. My name is Yoon, and I'm from SNU. I'm going to present our new synthesis method that utilizes static analysis. This work is co-worked with Woosuk Lee and Kwangkeun. Our target is inductive SyGuS problem, where a syntactic spec is a grammar and a semantic spec is a set of input-output examples. Suppose we want to synthesize a target function f that turns off all bits from the first bit to the rightmost 0 from a given forbidden integer. The SyGuS problem and its solution are as follows, and I will use these examples throughout this talk. The popular top-down strategy searches for the unknown target function by starting with a partial empty program and then gradually filling the in-program holes. For example, we can fill in the initial hole with x, or we can fill in it with right shift or plus. We can also fill in the left hole with another n, and so on. During the search, any infeasible partial program that can never satisfy the given examples is pruned. For example, a partial program x right hole can be pruned since no matter how we fill in the hole, the semantic spec cannot be satisfied. Then, how can you prune infeasible partial programs? There have been various approaches to pruning infeasible partial programs. One of the most popular approaches is to use static analysis. In this talk, I present our new synthesis method based on static analysis that can prune infeasible partial programs more precisely and efficiently. Our technique is based on forward-backward analysis and implemented in our tool called Simba. Simba outperforms the state-of-the-art tools in terms of both the number of solved problems and the running time. This performance improvement is due to a synergistic combination of forward and backward analysis. We'll provide more detailed results in the coming sections. Most of the previous methods based on static analysis are solely based on forward analysis. They symbolically execute each partial program using their abstract semantics and compute a sound over approximation of all possible outputs of programs derivable from the partial program. If the over approximated output does not subsume the desired output, the program can be safely discarded. Suppose our abstract semantics computes sequences of abstract bits of length 4 for a given partial program, where each abstract bit is 0 or 1 or unknown top bit value. Then, given the partial program x or whole, we can compute 1 top 1 1 as an over approximation of all possible outputs of programs derivable from the partial program. Since the over approximated output does not subsume the desired output, the partial program can be safely discarded. However, relying solely on forward analysis has a limitation. It just tells us the feasibility of partial program, but not about how to complete it. For example, the forward analysis determines that the partial program x XOR whole is feasible, but it does not tell us how to complete the whole. Backward analysis, on the other hand, can be used to derive necessary preconditions for the missing parts of a partial program, since it simulates reverse program executions. Given the desired output 0011, the backward analysis can derive that the whole of the partial program should be 1000. This necessary precondition over the whole can be used to check the feasibility of other partial programs derived by gradually filling the whole. For example, partial programs such as x XOR x right shift whole or x XOR x divided by whole can be pruned since they can never satisfy the necessary preconditions. We would not be able to prune them if we rely solely on forward analysis. To realize the synergy between forward and backward analysis, we need to address two challenges. First, we must find a good balance between the precision and the scalability of the analysis. Second, the backward analysis must be precise enough to derive useful preconditions for pruning. To address the first challenge, we combined several well-known and simpler domains into a reduced product domain. They are the bitwise domain and two interval domains. In addition, we found that using this domain, we could achieve sufficient synthesis performance without the need for more complex domains such as the relational domain. Here is an example to demonstrate how the reduction operator works. For simplicity, we'll focus on the bitwise domain and the unsigned interval domain. Suppose we have this product of abstract value, top 01 and 026. From the bitwise domain, we know that the unsigned bit representation ranges from 1 to 13. From the interval domain, we know that the first bit of the bit representation will always be 0. We can refine these abstract values by taking the mid operation on the reduction operation result. After performing the iterative reduction steps until reaching a fixed point, we obtain the best precision value within this reduced product domain. In this way, we achieved a pretty precise domain with reasonable cost. Thus, our solution to the first challenge is to use the reduced product domain. The second challenge is achieving precise backward analysis. To tackle this, we found that using concretized set of limited size enables cost-effective analysis. We refer to this approach as selective finite concretization. Let's consider this partial program with forward analysis result. Except for the input value x, the abstract values are top due to the presence of the hole. With backward analysis, we can obtain the necessary preconditions for the incomplete parts that contain the hole. However, the question is, how can we obtain more precise conditions? Let's consider the x times hole part. Since there is only one top bit, we know that the size of the concretized set will be 2, which is small enough to concretize. Thus, we can apply selective finite concretization on it. With these values, we can derive two equations because the input value x is also a concrete value. Since we are dealing with 4-bit integers and performing operations modulo 16, the traditional method of obtaining the unknown value through transposition is not applicable. Instead, we employ the extended Euclidean algorithm to determine the unknown value in this scenario. The resulting values are then joined into a single abstract value. As a result of concretization, the precision of backward analysis has improved. Hence, our solution to the second challenge is to the utilization of concretization. We realized our idea into a synthesis tool called Simba. The tool is publicly available on GitHub's repository. The following figure depicts the overall architecture of our synthesis algorithm implemented in Simba. The algorithm takes specification and initial partial programs as input. If there is at least one solution for the input, the synthesis algorithm generates a desired solution as output in finite time. In this section, I will demonstrate the step-by-step process of how Simba solves the running example problem. For a simple demonstration, suppose we have two initial partial programs. However, we may be given arbitrary set of partial programs actually. First, we perform forward analysis on whole x over x, right shift 1. Because the result abstract value is top, which assumes the desired output, we retain this partial program. Next, we perform backward analysis on it. Through the backward shift right and backward XOR operators, we obtain the necessary preconditions. Let's move on to the other partial program. The forward analysis reveals that the abstract value of the expression whole divided by x is 0, 0, 0 top. Because the right shift abstract value of 0, 0, 0 top is 0, 0, 0, 0, which does not assume the desired output, we can safely discard this partial program. For the next step, we run the bottom-up enumerator to generate a set of components which will be candidates to fill the holes in the partial program. Initially, we generate components of size 1, resulting in constant literals or variables. In this case, we have only two components, x and 1. Now we have a set of feasible partial programs and prepared components, so we move to the composition phase. In the composition phase, we aim to complete the holes in the partial program with components. By utilizing the necessary precondition, we can determine the feasibility of a component to the whole, considering whether the necessary preconditions assumes the component's value. In this case, the precondition is 110 top, but we cannot find any components with subsumed values. So with the combinations of current partial programs and component set, we cannot find the desired solution. So we invoke the bottom-up enumerator once again to obtain more components. Let's suppose that we have increased the desired component size to 3. After the bottom-up enumeration, we acquire some simple binary expressions as our components. During the component generation process, we discard redundant components with respect to the semantic specification. For example, we already have x with value 1, 0, 1, 1. We don't have to add redundant components such as x divided by 1, x and 1, because they are observational equivalent. This technique is essential and well-known in bottom-up searching, as it helps avoid combinatorial explosion. Returning to the composition phase with the grown component pool, we want to find components which subsumed by necessary precondition 1, 1, 0 top. Particularly, when we have sufficiently precise necessary precondition, we can efficiently identify the desired component by employing selective finite concretization and just looking up the prepared table instead of iterating on whole component pool. In this way, we discover one component, x plus 1, with output value 1, 1, 0, 0. Of course, the output value is subsumed by the necessary precondition. Finally, this candidate solution is the desired solution because it satisfies the semantic specification. For evaluation, we chose 5 benchmarks, which fall into 3 application domains. 2 benchmarks for branch-free B-factor manipulation, 1 benchmark for B-factor manipulation with branch, and 2 benchmarks for circuit transformation. 3 of these benchmarks were sourced from the SyGuS competition, while deobfuscation and lobster benchmarks were obtained from other research sources. We compared SyMBA against 2 existing general-purpose synthesis tools, Duet and Probe. Duet is the state-of-the-art tool for inductive SyGuS problems, employs a bidirectional search strategy. Probe, on the other hand, employs a bottom-up search approach guided by a just-in-time learned probabilistic model. The graph shows the fastest solver for each domain. In the majority of benchmark domains, SyMBA emerged as the fastest solver among all the solvers. This graph shows the number of problems successfully solved within a 1-hour timeout. In the case of branch-free benchmarks, SyMBA outperforms the other baseline solvers. However, for the branch benchmark, Duet performs better than SyMBA by solving additional 27 problems. The overall performance for each benchmark group is represented in these characters plots. For the branch-free benchmarks, SyMBA, the blue circle dots, shows the best performance. However, for the branch benchmarks, Duet, the green triangle dots, is better than SyMBA. To evaluate the effectiveness of our approach, we compared SyMBA to several variants, including brute force, or using SMT solver, and performing only forward analysis. The Texas plot clearly shows that incorporating backward analysis is crucial, as it shows the best performance. On the other hand, relying solely on forward analysis or using SMT solver proves insufficient in making the synthesis process faster. In some cases, those variants even underperform brute force due to the high analysis cost. In summary, our technique strikes a balance between analysis cost and pruning efficiency, resulting in improved synthesis performance. If you are interested in more details, please refer to our paper. Thank you, and I'm happy to answer any questions.
Thank you, Yongho. We have 5 minutes for questions.
Hi, thank you for the great talk. I'm Taeun from KAIST. You mentioned that you use concretization to improve the usefulness of the backward analysis. In the example, you showed us concretizing only when we had like one hole for the top. But in practice, how do you set like how much you can concretize? Like, is it as a parameter or is it learned?
In our tool, the value is parameterized. And the default value we used was 8.
8.
So, yeah.
Okay, thank you.
Hi, thanks, great talk. Are there particular grammars and operators that make this forward and backward analysis work really nicely together? And there are obviously grammars where you don't get this nice interaction?
Excuse me?
So like it's easy to do backward analysis over like a plus operator or something like that, but other kinds of operators, not so much.
Sound is a little bit howling, so I didn't get your question. Sorry.
Okay.
Maybe we talk offline.
Hello, Patrick from Purdue University. 2 quick questions. One was, I was wasn't super clear for me to me from the talk whether this generalizes to like component-based synthesis. So I'm thinking about operators where like they're user provided, or is this still applicable, or could this generalize to that? For example, if a user provides like a library of components that they would like to use for like component-based synthesis instead of like a fixed set of like bitwise operators.
It sounded only, so just a little bit distance from the mic.
Closer or farther?
Distance. Some distance.
And then just my second question was, I saw you compared against Duet. Have you looked at this, what I believe is the successor tool, like Trio? Or is there any like difference between Duet and Trio on your benchmarks?
Difference between Duet? Duet is those bidirectional search, and so Duet does top-down propagation and bottom-up search, but our tool just get the initial partial program, fix the initial partial program, and just do bottom-up enumeration and combining. So
yeah, so did you compare against Trio? Trio? I believe that was like some of the later work in this.
I don't know about that.
Oh, sorry, thank you.
Thank you.
All right. Okay, I have a very kind of high-level question. So there was quite a little bit of work by Hakio, his co-authors, on synthesizing imperative programs using abstract interpretation. So have you considered applications beyond the classic SyGuS domains such as circuit and bit vectors and something like imperative, heap manipulating programs using backwards abstract interpretation?
We are working on string domain in SyGuS format, but we do not have any plan to do more than over the SyGuS format. But,
all right.
Yeah.
Thank you so much. Other questions? Okay, if not, let's thank Yongho.
Thank you.